In this video, we're going to check out the intersections of two chords within a circle and look at some of the relationships that exist based on that intersection happening. All right, first thing I want to show you is we have two chords. I've labeled some things on here. So what I want to do is I want to look at this circle and see what we have so far. So far we've got these two chords are intersecting, and they create these two angles. We know this is a central angle. Here's the center point. And we know that these two angles here are vertical angles, so they're congruent. So what we've got is a situation where these two arcs are created, and these arcs are congruent because the central angles that project to them are congruent. Alright, so what we're really interested in this video is taking this intersection and moving it off of the center point and just kind of checking out what happens. If I move this intersection off the center point, notice what happens to the arc measures. Alright, so again, back onto the center point, we've got our arc measures labeled, and we're just going to slide this up, and let's check out what happens. A couple different things. Number one, notice that I didn't change the measures of these angles in here. So these angles are still congruent because they're vertical. But what happens is when we slide this vertex away from the edge of the circle, the arc that it projects to, or the arc that it subtends, becomes greater. So let me mark that arc real quick. So there are these little pieces right here that we kind of add into this particular part. But look at what happens. I can take this piece here and kind of rotate it so that it fits with the trajectory or the curve of this up here. And what you can kind of see, hopefully, is that that piece is going to fit pretty well in there. And it's not a perfect fit, but that's kind of the point behind this, is that we can take the piece that we added on down here. We made this arc measure greater, but we reduced this arc measure up here. And it happens to be, basically whatever you add down here to this arc gets subtracted from this arc. So we want to be able to relate this relationship to any situation. So anytime we have two chords intersecting, what actually ends up happening is this increases at the same rate that this decreases. So the arc measure increases down here at the same rate that the arc measure decreases up here. So we've got a smaller arc right here. And so now what we've got is a situation where we can figure out this angle measure, the measure of angle AED. That angle measure is going to be equal to the average of these two arc measures. Okay? So if C is now here, it's the intersection of those two things, and A and D slide out because we slid our intersection back. But we can write this expression, and we know that the angles that project to create these arcs are actually going to be the average, equal to the average of the two arcs that are created. So it's arc BC plus arc AD. Remember, we find the average by adding them up and dividing by however many there are. In this case, we have two arcs. So this is the general formula. And for this case, it actually works that these two angle measures, they're not congruent here, but they project to these arcs, and so that relationship still holds for these. All right, so this arc right here, or the angle measure on the opposite, is going to project to these arcs right here, which are going to have different measures because we're not on the center. If we move off the center, we're going to have different measures. I just messed up here. Hopefully you guys get the picture. But this arc right here and this arc over here, the average of these two arcs is going to give us the measure of the angle that projects to them. Alright, so we've got AC, arc AC, and arc BD. If we add those up and divide by 2, or take the average of those two arc measures, then that'll give us our angle measure that projects to them. All right, so the next thing we want to investigate is what happens to segment measures here. And what we're going to do is we're going to create this scenario. So again, we've got two chords that are going to intersect. We're going to prove that these two triangles are congruent. So CEA is right there. So I want to draw this side measure down. There's my one triangle, and my other triangle is BED. So we're going to compare it to that triangle right there. All right, so if I want to prove that, I need to start with the let statement. So let the diagram, that's spelled wrong, be given. We want to prove similarity because so that we can use those results to figure out ratios of the sides. So let the diagram be given. If I want to prove similarity, I only have to show that two angles are congruent. So let's go ahead and match up a couple angles. Hopefully the one that kind of jumps off the page to you are these two pairs of vertical angles. So my first angle argument is that the measure of angle CEA is congruent to the measure of angle BED. And that's because vertical angles are congruent. All right, my next argument here actually has to do with inscribed angles. And so I can match up either one of these. I can actually give an argument for either one of these. I'm going to do these two angles down at the bottom here and make an argument that those two are congruent. So my argument number one is that CAE is congruent to the measure of angle BDE. And the reason that I can say this is because inscribed angles, so I'm going to say since inscribed angles that project to the same endpoints and I'll show you what I mean here in a second. So here we have two inscribed angles that project to the same endpoints, and we know that that must be true, or it must be that those two things are congruent. So let's look at where these two things project. So here I've got, here's my one endpoint right here, here's my other endpoint. So this angle, this inscribed angle, has a vertex on the circle, and it projects to these two endpoints. Well, if I look over here at angle BDC, or BDE in this case, that angle also has the same two endpoints. And so if two inscribed angles project to the same two endpoints, then we know those two inscribed angles must be congruent. So by angle, I've shown that these two triangles are congruent. So the first one was CEA, or I'm sorry, not congruent, similar, and the other triangle is BED. All right, so if you think back to what we were doing, what we wanted to do was find some way to relate the segments of these particular chords. And so we started off with this scenario. We have these two chords, and it's CE. And if I'm going to match up CE with its corresponding part, it better be with BE. And because I just proved that these two triangles were similar, what I can do is write the ratios of those. I know that the ratio of CE to its corresponding side, which is BE, is going to be equal to the ratio of any other pair of corresponding sides. Well, since these are the other two corresponding sides in my diagram here, I can write that the ratio of these two things. All right, so the ratio of AE to, if I write it in as AE, I need to write this as DE and keep it in the same order. So here's really the point, is that anytime you have two chords that are intersecting or crossing, we can because they're going to be similar, and you can prove that for any two chords. Because they're similar, their sides are going to be proportional. All right, so we can use that to write a proportion and find missing lengths.